So, we talked about single particle shell model and then slight variation in that also, and we saw that it met success in some cases and limited success in some other cases. And then we took care of that pairing energy, breaking of pair, and we could explain some of the excited states, but still there were problem cases. So, one problem case that I discussed last time was calcium 41 and calcium 43. In calcium 41 you have, or calcium you have 20 protons. So, that major shell is completely filled, and then if it is calcium 41 you have 21 neutrons. So, 1 extra neutron, and if you have 43 calcium you have 3 extra neutron, and this will go in F 7 by 2, right, because after 20 you have that 1 F 7 by 2 which takes that magic number to 28. So, this in calcium 41 that one last neutron, and in calcium 43 3 neutrons, they will be in this 1 F 7 by 2, and we saw that the excited energy level structure was very different in the two cases. Whereas, if you go for the single particle shell model, only the last nucleon should contribute to the properties, and then they should be similar. Another case where this single particle shell model, even after taking care of this pairing, is difficult to explain, that I will show you on the screen. Okay, so, look at this diagram. There are two nuclei which are discussed here. One is argon 38 and another is 130 tin. So, just look at these diagrams. I will try to reproduce it on the blackboard, and then maybe we will discuss more, but first on this screen. Argon, what is the proton number? Z for argon. Little bit of a periodic table you should all remember. Argon is 18. In atomic structure, the shell, major shell closes at 8, 18, 36, so on. So, argon Z is 18, okay. Argon Z is 18 and the neutron number will be 20. So, that neutron shell will be completely filled, and you will have 2 less neutrons in that last energy level. Okay. So, remember this, and then you have 0 plus, then first excited state is at 2 plus at 2.17 MeV, then you have 3 minus and yet another 2 plus 3.95 MeV. So, if I draw it on the board and try to see from where these 2 plus 3 plus are coming, if we go by that shell model, so let us try to understand this. Okay. So, what is this is for 38 argon, this is for 38 argon, Z is 18 and N is 20. So, the lowest ground state is 0 plus. Okay. The first excited state is what? 2 plus. Spin parity is 2 plus, and this is at 2.17 MeV, and then you have 3 minus, and close to this you have another 2 plus. These are 3.77 MeV and 3.95. So, let us draw that level diagram, shell model level diagram. The lowest one is half, next one is 1p, then very good. So, by this time you remember all these at least low lying levels. Next
1d 5 by 2,
1d 5 by 2, then
S half.
2s half, then
1d3 by
1d 3 by 2. So, 2 here occupancy, 2 here, then 4 here and 2 here, that makes it 8, and then 6 here, 16 plus 18, how come?
4.
So, 6 plus 2 8, 12, right, 10, 12, 14, 18, 20, right. Then you have next
F7 by 2.
F7 by 2. So, these 20 neutrons will fill all these levels, that major shell will be closed there, and protons, you have only 18 protons. So, 18 protons means here you will have 2 protons instead of 4. The neutron is all filled. The neutron we are not discussing much. This is neutron, this side is, let us call it proton. So, you have only 2 protons here and 2 protons here and 6 protons here, right. This will be 6 protons, and this is all filled, right. So, what should be excited state? Where do you expect a excited state? How you will excite it? So, the obvious thing one would think that this last unfilled shell here, this is also S half is filled, this D 5 by 2 is filled, here you have unfilled shell. So, there are 2 places available here. This pair could be broken and this proton can be sent up. We need excited state energy levels. We have these excited state energy levels. We are trying to understand how this is appearing, how this is appearing, how this is appearing, and so on. So, if I pump energy in this nucleus to take it to excited state, what can happen? This P can go here. If this P goes here, you have 1 proton in this D 3 by 2. So, in D 3 by 2 you have 1 proton, and then you have 1 proton in F 7 by 2. Okay? No more pairing, because this is a single proton here and there is a single proton here. So, angular momentum when they combine, what will happen? You will have 3 by 2 and 7 by 2, they are combining. So, what are the possible values when 3 by 2 and 7 by 2 angular momentum combine? What are the possible value? 7 by 2 plus 3 by 2, 2, 7 by 2 minus 3 by 2 in steps of 1, J1 plus J2, 2, J1 minus J2 or J2 minus J1, whichever is bigger, and in steps of 1. So, this will be 7 plus 3 is 10. So, this is 5 and 7 minus 3 is 4. So, it is 2. So, 4 and 3, 5, 4, 3, 2. And what should be parity? Plus or minus? This will be, yeah, minus. One is D electron and one is D proton and one is F proton. Now, D is parity positive, F is parity negative, S, P, D, F. So, the combined parity will be negative. So, this can give this. So, probably I understand how this is coming. This 3 minus this level can come if this proton goes from this point to this point and they combine to give this 3 minus, right. Then you have 2 plus here and 2 plus here. How do I get 2 plus? Guess how do I get 2 plus? This is the ground state. Okay, this is the ground state. Then where should I take which proton? to get 2 plus, and that too in 2 different styles, one lower energy, one higher energy.
These go down into
Hmm?
S half.
S half, there are only already 2 protons, and it can contain only 2 protons. Nothing can come to this. What do I do? From S half to D3 by 2. Good. Yes, that's a good suggestion. If I take this proton here, which is possible, here you have vacant spaces, you can have 4 protons, up to 4 protons you can have here. If this proton goes here, then you will have 1 proton in S half and 3 protons in D3 by 2. This state is, you can generally people write it this way, configuration proton, right. This is for proton 1 and then 1d3 half, 1d3 half 3. People write it as -1. -1 means the full capacity -1. So, D3 by 2, this shell will be closed, this subshell will be closed if we have 4 protons here, 1 less. So, these are called hole states, 1 hole in this D subshell, does not matter. So, if this P goes here and we believe that this pair is still intact, okay, this pair is broken and then this proton goes here, this pair is still intact, that means they are combining to 0 plus. Then you have 1 proton in S half, another proton in 3 half. So, 3 half and 1 half, and these can combine to 2 or 1, and parity positive, S is also positive, D is also positive. So, parity positive, 2 plus and 1 plus. So, one of these 2 plus can be obtained in this fashion. What about the other 2 plus?
2.17.
One of these 2, with this one or this one, that calculation is needed to see whether this 2 plus corresponds to this or it corresponds to this, and in fact, it is most likely it corresponds to this 3.95. So, this way, breaking here, taking here and recombining to 2 plus, that in fact goes here. This remains difficult to explain in terms of this shell model. All right. Now, take another example. Look at the screen. On the same slide, you have tin 130. So, for tin, Z is 50 and therefore, N is 80. And look at this, you have 0 plus ground state as expected, because this is even nucleus, Z is even, N is even. So, ground state is 0 plus, and then you have the first excited state is at 2 plus. Same was the case with argon 38, the first excited state was 2 plus, here also the first excited state is 2 plus, and this is around 1.2 MeV. And then you have a series of energy levels, 7 minus, 4 minus, 2 plus, 5 minus, and so on, so on, so on. Many of them. All right. So, if I draw this diagram also on the board and try to see if we can understand it with a shell model scheme. So, tell me what it is. This is for tin 130. So, 50 here and 80 here. 50 is shell closure and 80 is 2 neutrons less than that major shell at 82. So, tell me what is there on the screen, the energy levels 0 plus, 2 plus, and then you have many of them. Actually, I have not drawn all of them, you have several, and you have varieties of spin parity things, 4 plus 2 plus 5 minus and so on. I am not doing one correspondence, there are several. Now, to understand this, I have to draw a similar level scheme up to 82. Up to here it will be 28. After this 1f7 by 2. After that what it should be? Huh? What it should be after 1f? 2p3 by 2. Yeah. That say this 2s is here. So, in that 2 series, after 2s you will have 2p, and 2p will split in 2p3 by 2 and 2p 1 by 2. And since this f7 by 2 is here, there should be a corresponding f5 by 2. So, one series will give you f5 by 2, and this 2 series will give you 2p 3 by 2 and 2p 1 by 2, and 3 series will not start yet. That will come. Wait. I am talking of this principal quantum number. So, one series is 1d, 1f is already here 7 by 2. So, 1f 5 by 2 over, go systematically. 2 series, 2s here, therefore, 2p in the next shell, and since 2s has been introduced here, so 3s will not be introduced here, it will introduced in the next measure shell. So, in this shell you will have just this 2p 3 by 2 1 by 2 and this 1f 5 by 2, right, that is all. Okay. So, after this 7 by 2 we are writing, so you have this 2p 3 by 2, 2p 3 by 2, 1f 5 by 2 and 2p half, right. How much is this? 4 here, 6 here, 2 here, and what is missing? Is something missing? Yeah, from the next measure shell that 1 will come down. So, you have already 1f here, so 1g, right. So, 1g 9 by 2 will come down and join this shell. So, 1g 9 by 2. 10. Now, it is 22. So, 28 plus 22 is 50, right. What will be the next shell? Look at systematically, one series, principal quantum number 1, 1g 9 by 2 here. So, 1g 7 by 2 should be there. So, 1g 7 by 2. 2 series, 2p is here. So, 2d should be here. So, 2d 3 by 2 and 2d 5 by 2, 2d 5 by 2 and 2d 3 by 2. So, 2 is over 3. Now, since 2s was introduced in this shell and 2p here, so 3s will come here, 3s half. So, 3s half will come here. So, if you remember this logic, even this complex diagram you can construct, and you do not have to cram all these levels. So, then 3s. So, that 3 series is here, all right. So, 1 we have taken care of, 1g and 1g, 2 we have taken care of, 2p here, therefore, 2d, and 3 we have taken care of, and 4 has not yet started. And from the next one, this 1 series will come down, larger j value of, so 1 h 11 by 2. So, 1 h 11 by 2 will come down. So, that will be next measure shell. So, you have 8 plus 6 14, 18, 20, 32, and 50 plus 32 is 82. Okay. Next measure shell will start at h 9 by 2. So, if you remember this logic and do it systematically, remember your principal quantum number 1, so 1s, the lowest most. Then next shell 1s, so 1p, and if 1s has come here, in the next measure shell 2s is not going to come, it will come next to next. So 2p, just this 2p. Then 1p, so 1d in the next shell, and 2s will now come. It comes alternately, 1s comes here, then 2s comes here alternately. So this measure shell complete, and from top 1 is coming down. So 1f comes down, but does not join this, you have a gap. The lowering is not so much that it can join this. So in this case it is standalone f7 by 2. And then next look at 1 series, 1f here, so 1f 5 by 2 will go there. Then 2 series, 2s here, so 2p will go there, and 3 will not start yet because 2s has just come here. So you have constructed this measure shell, and same logic go ahead, right, same logic go ahead. 2s had been in that previous shell, so 2p will be here. 1 f was there, so 1f will be here, 1f 5 by 2 will be here, 2p, right, and 3s will not come, 3 will not come, and therefore, and from the next this g9 by 2 will come down and join the shell. So this is done. Next one, 1 series n equal to 1, so 1g9 by 2 here, so 1g7 by 2 here. 2 series, 2p is here, so 2d is here. 3 series will start, so 3s here, and then from top h will come down and join the shell. So this way you can construct this one, this way you can construct the second one, 126 will be the shell closure, and so on. So now look at that tin 5080. So protons will fill the measure shell up to 50, so that is okay, and neutrons will be 2 less than this measure shell. So all this will be filled. You will have 2 neutrons here, you will have 4 neutrons here, and you will have 10 neutrons here. In place of 12, you have 10 neutrons here. So 2 less than this measure shell. So this is ground state, these are all filled, right? These are all filled neutrons, and protons of course they are filling up to 50 and just staying intact. So this is the ground state of tin 130. And then you have a 2 plus here, and then many minus parity and many plus parity, and 2, 4, 5, 7, many things coming in. So let us try to understand if energy is given, and all this these energies that you are seeing, it is around 2 MeVs, and this is around 1.2 MeV, 2 or 2.5 approximately, remember. So this measure shell gap is too high, right? This measure shell gap is too high, and at this low energy you do not expect that it will go to that shell. You can think of that, then one will be H9 by 2 and one will be H11 by 2, but the energies will lie too high. So how do I excite it? We break this pair and take it here, but even typically breaking a pair needs something like 1.5 MeV, 2 MeV type of energy, or when a pair is formed, this much energy is saved, energy of the nucleus is lowered if the nucleons pair, and that amount of energy saved, or if you want to if you break the pair, amount of energy raised is typically of the order of 2 MeV or so, 1.5 2 MeV. So breaking a pair itself is a bad scheme for this 2 plus state, right? It is at 1.2 MeV. But anyway, if you break this pair, what you will have? You will have a neutron in 1 by 2 and in unpaired neutron in H 11 by 2. So, this is in H and this is in S. So, if they combine, what are the possible values? 6 and 5. And what is the parity of H? Plus or minus? Parity of H, parity of S is plus, parity of H, this one minus, right, plus minus plus minus plus minus, and therefore, the combined thing is minus. So, this 5 minus is picked up, right, and the kind of correct energy also somewhere around 2.5 MeV around. So, breaking a pair and taking it up. So, this 5 minus we understand from where this is coming. What else? What else we can do to get the other ones? D
Down, come up.
right. Okay. So, we break this pair. If this has to go, this has to go here. 3s half is already full. Here you have a space. So, it can be broken and from here it will be taken there. So, then what is the scenario? Then you have D 3 by 2 and H 11 by 2. This will given 7 to 4. 7 6 5 4 and again negative. So, you have this 7, look at this 7 minus. So, this 7 minus can come through this mechanism, right. If you find any 6 minus 5 minus 4 minus in this range, that can come through this mechanism. What about 2 plus? How do you get 2 plus? One possibility is break a pair, do not take one of them to the upper state which we were doing so far, recombine it in some other final J. Pairing means if I have, for example, suppose I take 1 neutron pair from here, you have 10 neutrons, so 5 pairs. So, let us say I take one such pair. So, I have 8 neutrons, they are all paired, and then I have 2 neutrons which is also paired. I break this pair. They are paired means whatever J, this 11 by 2 and 11 by 2. Individually, if I see this neutron, its angular momentum is given by 11 by 2, H 11 by 2, J is 11 by 2 and H. So, L is 5 plus half will give you 11 by 2, and the second neutron is also same. So, now this 11 by 2 and this 11 by 2 is adding to 0, that is the meaning of pairing, 0 plus, this is giving me 0 plus. Paired means their angular momenta are joining to give you 0 plus. Plus anyway it will be, 2 of them are in the same state. So, it will be plus whether it is odd L or it is even L, and they are combining to 0, J equal to 0, that is the meaning of pairing in which the energy is lowest. But these 11 by 2 and 11 by 2 can combine in many different angular momenta also, 11 by 2 and plus 11 by 2. What are the possible J values? Plus 11 by 2 plus 11 by 2 will be 11, and 11 by 2 minus 11 by 2 will be 0, and in steps of 1, right. This is what you do, you expect, but there is a catch. We will talk about that. Just after a minute I will talk about that. But what I am saying is, when I say that these two neutrons have paired up. That means they have chosen out of this list this 0. That is the meaning of pair. The energy will be minimum if they combine to give you this 0 plus. Energy will be this will be all plus, everything will be plus, because you have 2 neutrons in the same state. So, even if they are negative parities, 2 neutrons with negative parity combined, negative into negative is positive. So, this is this. So, the energy is lowest when they combine to 0 plus, that is pairing. But if we say that okay, we break the pair and recombine them not in 0 plus, but something else, the energy will be higher. So, that will be an excited state, right. If I break the pair and recombine in the same this H 11 by 2 subshell here only, I do not take this after breaking, I do not take this neutron somewhere else, it still remains here. But the angular momentum combination no more gives me 0 plus, it gives say 2 plus or 4 plus or something else, the energy will be higher, that means it will be an excited state. So, that is also a possibility. Okay. And the catch I was mentioning is that yes, the rule says if you have a J1 and if you have J2 and if they are combining, they can give you from J1 plus J2 to J1 minus J2 or J2 minus J1, whichever positive, in steps of 1, that is the rule. But here an additional feature comes, if 2 neutrons are sharing the same N and N, L and J, then they are identical particles, the 2 neutrons, identical particles, and these quantum numbers are already fixed, N, L and J1, J2, they are already fixed. So, you have to bring in those identical particle quantum mechanics. They are identical means you cannot distinguish between which one is the first particle and which one is the second particle. Then you have less number of states allowed, or you can say the wave function has to be symmetric or antisymmetric, identical particles. Okay. So, that restricts the number of J values which result from here. I will give you just an example which also will be used in our later discussion. Suppose you have 2 angular momenta to be added, 2 and 2, J1 is 2 and J2 is 2, and suppose they are identical particles, 2 identical particles. This is 11 by 2, 11 by 2 we are talking, but to keep the things simpler, let me suppose J1 is 2 and J2 is also 2, and 2 identical particles are occupying these, right, and then they are combining. So, in principle they can combine to J1 plus J2, they can combine to 4, 3, 2, 1 and 0 in principle, but let us see. You know, Mj will be equal to Mj1 plus Mj2. So, let me write Mj1 this side and Mj2 this side. What are the possible values of Mj1? 2, 1, 0, minus 1 and minus 2. And what are the possible values of Mj2? Again 2, 1, 0, minus 1 and minus 2. All right. Let me put the dots and then I will say why I am putting these dots. So, I have put these dots. Now, the dot here means I am talking of Mj1 equal to 2 and Mj2 equal to 2, right, fine. Then this dot means Mj1 is equal to 2 and mj2 equal to 1. Now, correspondingly look at this point, mj2 for this one, mj2 is 2 and mj1 is 1, and for this point here, mj2 is 1 and mj1 is 2. The only difference is that the labels are interchanged. One is 1 and other is 2. So, here the first one is 2, the second one is 1, mj1 and mj2. For this, the first one is 1 and the second one is 2. That is the only difference. These two cannot be counted as two different states. They are identical particles. You cannot say that this was in mj equal to a, for this particle mj was 2 and for this particle mj was 1 versus the opposite one. If there are identical particles, you do not know this particle and that particle, you only know that there are two particles, finished, right. So, these two should be counted as 1. Other way also you can think, if they are combining, what is mj for these two? Mj equal to mj1 plus mj2. So, mj will be 3, right, 2 plus 1 3, here also 2. So, if mj is 3, you have two different possibilities, this is 2, this is 1 and this is 1, this is 2, and you have to take only the symmetrical ones. You remember that spin half and spin half combining to capital S equal to 1 and capital S equal to 0. So, if mj is equal to say minus 1, right. So, both should be minus half, good. If that is plus 1, both should be plus half and plus half, but if that is 0, z component of the total capital S is 0, there are two possibilities. One possibility is this is plus half, this is minus half, or that is minus half, this is plus half, but then we cannot distinguish between them. So, we combine and say that okay, spin up spin half plus spin minus the opposite one, we make symmetric or antisymmetric combinations, right. So, for identical particles you have to do this. So, in this scheme I will count this and I will not count this, I cannot count them as two states. Similarly, this 0 here, this point here, this is all right, and this point here. Look at this 0 and 2, look at this 0 and 2. So, it is only the difference of labeling, otherwise it is the same. So, if I say that one particle has 0 and another particle has 2, not first and second, one particle has this and one particle has this, which one we do not talk about that, we have to combine the two. So, this I will take and this I will not take. Similarly, if this I take, this I will not take, if this I take, this I will not take. This is all right. Here we first particle or second particle, one particle has 2 and another particle has 2, the total is 4. Okay. Similarly, so all these diagonal things will be, I will be counting them, I will taking them as different states, and all these I will be taking, and all these I will not be taking. It is only repetition, the cross one are repetition of the dot ones. So, only one of the two have to be taken. So, number of states get limited once you impose this identical particle business. This we did not do earlier. Earlier when we said that we are combining this and that, all possible j values from this rule we had taken, because we used to put one of the neutron in some other state. So, now they are not sharing the same quantum numbers. if I put for example this neutron here and combining these two, then L is different. For this L is 0, for this L is 5. So, in that case that identical particle, that rule will not come. So, if you have two similar particles in that same level, same J, same L, right, and then you are combining it, then you have to take care of these things. So, now if I write what is that mj, this mj, the values, here it is 4, here it is 3, here it is 2, here it is 1 and here it is 0. Just for counting business, here it will be 2, here it will be 1 and here it will be 0 and here it will be minus 1. Then this one 0 plus 0 is 0 here and 0 and plus minus 1 is minus 1 here and minus 2 here, and this one minus 1 and minus 1. So, minus 2 here and minus 1 here, minus 3 here, okay, minus 3 here, and this one is minus 4. So, if I take these mj values, if I take these mj values, they will correspond to j equal to 4. For j equal to 4, you should have mj equal to 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. And then of the remaining, if I take these ones, that gives me 2, and then only 1 is left, mj equal to 0. So, j is 0. So, you see that 1 and 3 are not allowed. Normally, if you have 2 and 2, you should get 4, 3, 2, 1, 0. So, only the even ones are. So, here also 11 by 2 plus 11 by 2 will not add to 11 plus, 10 plus, then 8 plus, then 6 plus, and then 4 plus, and then 2 plus. So, this type of manipulation is also possible, where we break a pair and then recombine in the same energy level. We do not take any particle up or down, only recombination of angular momentum in a different final state, and from there I can think that I can get this, for example, this 4 plus probably I can get, this 2 plus probably I can get, but still this 2 plus will be a mystery. Okay. This 2 plus will be a mystery. You have 1 2 plus here. So, if you think that 2 plus is coming from here, that 2 plus is here. Now, it is not because of this particular structure of nucleons here, these energy levels here, or in case of argon 38 we had a particular configuration, and then we were trying which neutron or which proton to take where and how to combine and get all these energy levels, because these are not just two cases. These are examples of a wide class of even nuclei. Almost all nuclei, even nuclei up to capital A less than 150 or so, and little bit beyond the very heavy nuclei also. All even hundreds of even nuclei show a 2 plus state as the first excited state, right. So, it is not that by doing some kind of pair breaking or some kind of excitation from this level to that level of that last nucleon, or say last valence nucleons, you can get that. Hundreds of nuclei having very different values of Z and N, even nuclei, they all show the first excited state as 2 plus state, and the energy of that 2 plus state shows a very systematic variation as a function of A. So, but you know, if you just change neutron number by 1 unit or proton number by 1 unit, it will occupy some very different state in this shell model energy state scheme, right. But then the energy of first thing is all of them are giving the first excited state as 2 plus, and the second one is that energy of that 2 plus is very systematically changing with capital A, even though the occupancy of those shell model levels is very, very different. We are talking of a range of nuclei now, and proton number or neutron number going up by 1 unit or 2 unit changes the whole level scheme. So, this systematic variations show that the shell model is okay, and all these occupancy by neutrons and protons are okay, but somewhere in some of the phenomena not one nucleon or two nucleon is deciding it, maybe a much larger number of nucleons. So, we are going away from the shell model. Maybe some a larger number of nucleons, or maybe the whole nucleus is participating and giving you those properties. I will show you two systematics on the screen for these even nuclei, and you see what it is. This figure is taken from that Crane book, and it shows you on the y axis side, it is energy of that first excited state, which is 2 plus. This is energy of the first excited state for these even nuclei, and that first excited state is 2 plus, and this point that you see here is 1.0 MeV, if you are not able to see that printed thing, and this point here, this is at 2.0 MeV. So, this is energy of the first excited state, and that excited state is 2 plus. We are talking of only even nuclei, and these are the measure shells closure. This is n equal to 50, this is n equal to 82. So, these are say close to those closed shell things. This is 82 here, 126 here. So, at those shell closure suddenly it goes up, right. So, the shell model is not to be discarded even here, the shell effect is being shown. When the measure shell closes, that excitation energy is very high, but then it systematically decreases. Okay, you can see it systematically decreases in between these closed shell nuclei. Focus your attention here. This point here is A equal to 150. This side is A, nucleon number. Even nuclei we are talking, do not include odd A nuclei in this diagram. So, this point is 150 and this point is 200, A equal to 200, and this range capital A going from 150 to 200, you look at the energy of the first excited state, it is so low and remarkably constant, it is almost constant here, and very low. If you plot on this diagram y axis, it will be somewhere around say 100 kV or so, much less than 1 MeV. This is 1 MeV, this is 1 MeV line, and this is here. So, maybe 50 kV, 70 kV of that type, less than 100 kV. So, this, and then again it increases, and here again it goes down. So, keep this in mind, we will need this in discussion. Okay. So, the way all these even nuclei, you can see how many of them are shown on this graph, maybe hundreds of them. Here is a nucleus, here is a nucleus, here is a nucleus, here is a nucleus. So, in this much of area I can see 1, 2, 3, 4, 5, 6, 7, 8. So, in this whole diagram that is drawn, hundreds of nuclei are there, and for all of them the first excited state is at 2 plus, and the energy is around, if I take this average line, say 1 MeV. Closed shell, near closed shell, it goes up to around 2 MeV, but most of the time it is around 100 this 1 MeV. And for this particular range here, this particular range, it is very small. Okay. Now, next systematic is the first excited is 2 plus, and then above that you have a 4 plus state, not necessarily second excited state, it could be third, it could be fourth, it could be fifth, but if you search, then above this 2 plus, the lowest 2 plus, you will find a 4 plus also existing somewhere, right. And if you look at the energy of that 4 plus and divide it by the energy of lowest 2 plus, this is the diagram. This is energy of the first 4 plus appearing from the bottom, and divided by energy of the first 2 plus state, 2 plus level from the bottom. This is the first excited state anyway, and this E4 is the first 4 plus that you find above this 2 plus, and that ratio is plotted here, and this is the 0.2. This ratio is dimensionless, this is the 0.2. So, you can see most of them are crowding around this 2. Closed shell effect is there, this is closed shell. So, at closed shell this ratio goes down. So, closed shell effect is there, but if you are away from the closed shell, where these magic numbers are not there, n is equal to 50 is here, this is n equal to 50, this is n equal to 82, this is n is equal to 126. But if you are not very close to that, most of the time you see that the ratio is around 2. And where is our 150 to 200 range? It is here. Capital A equal to 150 is here, and capital A is equal to 200 is here, and look at it, the ratio is, this is around 3.3. Right. This ratio is 2 here, this line is 3 here, and here see almost constant these ones, and the ratio is 3.3 here. So, this 150 to 200 is something special. Then this is beyond 220, this also joins the group, here also the ratio is around 3.3, but up to 150 here, these ones, it is around 2. All right. So, keep this in mind. Next lecture we will be discussing that above all these shell model levels and all those things, what other things are there which involved not just 1 or 2 or 3 last nucleons in that energy levels, but many more nucleons, and maybe the whole nucleus itself, the motion of the whole nucleus itself in a cooperative fashion, so that these systematic trends 2 plus and 4 plus and ratios, these things can come up.